Okay, so next thing we're going to talk about is similarity in right triangles. So I know we talked about similar triangles last quarter, and now we're going to talk about specifically similarity in right triangles. So our right triangle similarity theorem states that if the altitude is drawn to the hypotenuse of a right triangle, so remember an altitude creates a 90-degree angle, then the two triangles formed are similar to the original triangle and to each other. So if we look at the diagram on the right, if we just look at our main large triangle, which is A going to that right angle, B, C, so that we can say that triangle ABC is similar to, let's look at taking out that. So again, we're going to go A, but we're going to go this way, D, B. That is similar to triangle ABC. And then we have this tiny little triangle right here. And so we have B, D, C. And you'll notice, ooh, that was weird. We are going in like the same direction. We're starting on the longest leg and then ending with the hypotenuse. Okay, so that allows us to name our similar triangles. So if we want to identify the similar triangles in this diagram, I'm not going to sketch them, but let's just name them. And then this allows us to use those properties of similar triangles. So if we look here, I'm going to start with my longest side, PQR, triangle PQR. And that is, sorry, I got so used to writing congruent, similar to, then I'm going to do this next, PSQ, and then my little triangle, which would be QSR. So what I always do is try to find a starting point. I really like the starting point of starting with the tip of the longest leg that goes down to the right triangle or the right angle. So that just helps you so that you keep it consistent. Okay, so now let's use that. We're going to find the value of x. So let's look at our similar triangles here. We have this large one where we have all the sides. So we are probably going to use that. And then we're trying to find this value of x. What we have here is we can either do the small triangle because it's a leg of the small triangle, or we can use this triangle, this medium triangle, because it is also a leg of that medium triangle. So we want to set up a proportion, but the first thing that we have to do then is I can't talk. We want to make sure we have a leg and the hypotenuse. Let's go with the medium triangle. Sorry, that's what I'm trying to say. So the leg and the hypotenuse. So we're going to go leg over hypotenuse. And then if we look at our big triangle, we want to find the corresponding leg. So you'll see that it's the shorter leg, which means that that's going to be 9, the shorter leg, over the hypotenuse, and the hypotenuse of our big triangle is 15. And now we can cross multiply to solve. So we have 15x equals 108, which means that x equals 7.2. Okay, so let's look at this next one. Oh, my screen got bigger, but I like it. All right, so we have a leg here. With our medium-sized triangle, we have a leg and we have a hypotenuse. So we have a leg over hypotenuse. And then let's look at this big triangle. And we have the small leg over the big hypotenuse, which is 25 here. And then we solve. And so we solve for x and we get x equals 6.72. Okay. Now let's talk about our geometric mean. Ooh, sorry. All right, so the geometric mean of two positive numbers a and b is the positive number x such that a over x, I don't know why it wrote it like that, equals x over b. And so that means that if we cross multiplied, that x squared equals a times b. And so if we just wanted to find x, that means that x equals the square root of a times b. And that is really our geometric mean. So if we wanted to find the geometric mean of 6 and 30, then that means we're just taking the square root of 6 times 30. 6 times 30 is 180. And so that means it's 13.4. All right, 12 and 50, again, we're just taking the square root of both of those numbers multiplied, which is 600, and that is 24.5 when we round. All right, how are we going to use this? Well, of course, we are going to use this with two theorems for this section. The first one is our geometric mean altitude theorem. And so you'll see our altitude here is BD, and what this theorem states is that the length of that altitude BD is the geometric mean of the lengths of the two segments. Our two segments that we're talking about are this segment here and this segment here. So that formula is BD squared equals AD times DC. Now it's super easy to see on this picture, right? But sometimes maybe our picture will be a little bit different. So what you want to always do is locate that altitude, BD, and remember you're going to square that, and it's going to be equal to the two pieces that make up where the altitude makes that 90-degree angle. So let's look at our examples. We want to find the value of x, which is our altitude. So you'll see that our altitude goes here. We know that's an altitude because it creates that 90-degree angle. That means that these are our two pieces. Okay, so x squared equals 8 times 12. And that means that x equals the square root of 96. And that is about, ooh, I put that in my calculator wrong, sorry. That is 9.8, about. Okay, let's look at this next one. It's a little bit harder. You'll see this is our altitude. And we have the whole thing, but we don't know this little piece. But what we do know is that this whole thing is x, which means that little piece is x minus 30. So let's set this up. So 21 squared is equal to our piece, which is 30, times this little piece, which is x minus 30. And then we distribute. So 21 squared is 441. Sorry. And that equals 30x minus 900. I should have known that. Okay, then we add 900 to 441. And then divide by 30. And we get x equals 44.7. And there's our answer. Okay, so that was our geometric mean altitude theorem. And now we have our geometric mean leg theorem. So the length of a leg of the triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse adjacent to the leg. Woo! Okay, let's look at this. We're talking about the leg of our main big triangle. So if we look here, we have this leg, which is AB. Oh my gosh. Sorry. This, I don't know why that must be where that line is on my computer. Okay, this is AB. So this is a leg. So if we wanted to define this geometric mean leg theorem for AB, that would be AB squared. And it says it's the length of the hypotenuse, which is AD, and the segment of the hypotenuse adjacent to the leg. So that's going to be AB squared equals AD times AC. So it's the hypotenuse, which is AC, times the segment of the hypotenuse adjacent to the leg, which is AD. All right, that's when we're talking about AB, but we have two legs. So now let's talk about BC. So again, BC squared. And the hypotenuse on this one, again, will be AC. But the segment that is adjacent to that is now DC. I should have probably written those in the same order, but this is how it was in my notes. So you can switch them around if you want. It doesn't matter. It's multiplication. We can switch around. Okay. So we are now going to use those two equations to solve this next problem. All right, so you'll see in this one, we are given an altitude. I'm going to use that altitude theorem, the geometric mean altitude theorem, to find x, because I can see that with the altitude, remember it's those where it comes down to those pieces, and then we can find z and y using our leg theorem. Okay, so I know that 8 squared is equal to x times 20. And so that means that x is 64 divided by 20, and that gives me 3.2. So that means that whole hypotenuse is 23.2. All right, so now let's find z and y by using those leg theorems. So let's first find y, which again, we don't need that altitude, but it's going to be this. And so it'll be y squared. And it's going to be, remember, the entire hypotenuse, which you just said was 23.2, times that piece that's adjacent to it, which is 20. Because that is touching. Remember, adjacent means it's touching. It's touching that piece. Okay, so when we plug that into our calculator, we're going to get y squared equals the square, y squared equals 464. So that means y equals the square root of that, which is about 21.5. All right, let's do the same thing, but let's find z. All right, so z squared is going to be equal to that whole hypotenuse, which is 23.2, times the little piece that's adjacent to z, which is x, which we know to be 3.2. I didn't finish writing that up here. There we go. Sorry. All right, so 23.2 times 3.2 gives us 74.24. We take the square root of that value, and that means that z is 8.6. And now we've used our geometric leg theorem, our geometric mean altitude theorem to solve both of those problems. Yay, trigonometry's next.